and sigma square as the variance. Yeah. So secondly, and we can maybe give it here denoted as sigma 1, yeah, because it's related to the first asset. Then we have the second asset, let's say these small stocks. Now we have here, let's note there's small stocks, and we have here a portfolio of big stocks, y2t, which are the excess returns of the second stock at time t. Then we have here an alpha 2 plus beta 2 times xt plus epsilon 2t. Yeah? So again, this second equation here is a simple regression model, obviously, yeah, where beta 2 measures the exposure of the second asset against our market factor. Yeah? Our alpha 2 measures the unexplained part of the return of the second asset, yeah? And our E2t, epsilon 2t is the unsystematic part, yeah? Residual term. So, and again, we can say our epsilon 2t follows a normal distribution with zero mean and sigma 2 squared as corresponding variance. Yeah. So now we have defined our models here. We know that in vector notation, that's a t by 1 vector, that's a t by 1 vector, yeah. X is also a t by 1 vector, our epsilon 2 is a t by 1 vector, epsilon 1 in vector notation, it's a t by 1 vector. Yeah? So it's the same basically that we have discussed already in previous lectures. So again, what we have here in common obviously is that we have the same regressor here in the model. And that's typical for seemingly unrelated regression techniques, yeah? That each equation has the same set of regressors. Of course, we could also have here more regressors. Yeah, this is now the CAP-M case, yeah, where we have just one single factor. We could also add here the Farman-French. If you want to investigate the Farman-French 3-factor model, we would add here 2 more independent variables. Yeah, so it doesn't change. The methodology is straightforward the same. And of course, also this dimension here can be expanded. This is the case where we have just 2. N is 2. Capital N. So, and of course, it can be also 30. If you read the Farman-French papers, they usually have 25 test assets. Yeah? Then capital N is 25. Yeah? But we want to keep things simple. So why do we need this multivariate model? Why do we need to have this multiple equation model? Yeah. So obviously the covariance matrix, we have here obviously 1, 2, 3, 4 parameters in this model. So our parameter covariance matrix looks now like this. Yeah. So we have the variance of our alpha 1. We have the covariance of alpha 1 and beta 1. Yeah. And we have here, of course, the covariance between beta 1 and alpha 1. We have the variance of beta 1. We have the variance of alpha 2. And here on the last element on the main diagonal is the variance of beta 2. Yeah? So we have here obviously many covariances and variances going on. So that's a 4 by 4 matrix. Yeah? Because we have 4 parameters. Yeah? So, and the thing is that these alphas here, if we test them jointly, we have also to take into account the covariance. Yeah? There's obviously a covariance between alpha 1 and alpha 2. Covariance between alpha 1 and alpha 2. So, and because they are correlated, potentially correlated, we don't know that yet, we have first to run the model, but because of the covariance between these two guys here, yeah, if we want to test them jointly, we have to account for the covariance. Yeah, because the covariance matrix is of this model here is much bigger, yeah? And it has a lot of covariances on the main diagonal, above and below the main diagonal, whereas on the main diagonal we have the variances of our point estimators. Yeah. So that's the reason why we have to have this multivariate or this multiple equation model, and why we have to test those guys here jointly. Yeah. So in a typical asset pricing test, yeah, we're interested in how good does the model explain our returns. If our model performs very well, or if our model can price our test assets on the left hand side perfectly, then obviously these guys here should be jointly 0. Yeah, these guys should be jointly 0. And how we implement this test, yeah, this is what we will now discuss. And some of you might have taken the Research in Financial Markets course, yeah, and there we have been talking quite a lot about the GRS test, but now we will do it a little bit more in detail, because it's such an important test which is used over and over again in all of these, in many research papers. So once again, let's take this away. So our null hypothesis, under the null hypothesis, we want to know if alpha 1 is 0 and alpha 2 is 0. So under the null hypothesis, we assume that our model here, in this case the CAPM, is able to explain or is able to price our test assets correctly. If this is the case, obviously these guys here should be 0. Yeah? Because if this is the case, then the market factor can fully explain, or the exposure against market factor fully explains the return evolutions of our assets. Yeah? So under the alternative hypothesis, H1, at least one alpha I is unequal to 0. Yeah? And I is now 1 and 2. Yeah? So H1, the alternative hypothesis, at least one alpha I unequal to 0, and I is 1 and 2. We can also employ vector notation, yeah, because we like it so much. So we have here our alpha 1, alpha 2 in a 2 by 1 vector is equal to 0 and 0, yeah? Which is also a 2 by 1 vector because n is 2, obviously, and we can denote this vector as q. Yeah? Let's denote q, small q, as our vector of zeros. Yeah? And again, when the dimension is larger, obviously these guys here would be then also larger. Yeah? It depends on how many test assets we have. If we have 30 test assets, then obviously this guy would be a 0 vector that has 30 0 entries. Okay, very simple. So q has the dimension n by 1. So let's take this away now. As I told you earlier, you have to write fast here in this course. So let's take this away now. We know now our hypothesis. So how does the test statistic look like? Okay, let's take this away here. We know what we are talking about now, right? So this is now important. How does our test statistic look like? Again, it's defined as lambda, and it's now a very long expression, lambda, parentheses open, r, beta hat minus q transposed r, parentheses open, x, and then we have this. It's not a hat, it's like a q transposed. We will check later what's going on here, times, this is the big sigma, capital sigma hat, inverted, Kronecker product, identity matrix, dimension t, close this parenthesis, times again this x, which has a q above it. It's not a hat. We will define later what it is. Times r transposed inverted. So we see that this whole term here is inverted, times r times beta hat minus q, parenthesis closed. So this is a very long equation, and whenever you read econometrics books, they use a lot of these tests. It's called Wald test as well, and depending on the model, the test looks always somehow the same. If we have multiple equation model, then obviously we have this block matrix here, what we will define very soon, you will see, and this guy here, So we have here a lot of block matrices, and if we have single equation models, these are basically then the standard regression matrices. But in this case, obviously, we have a multiple equation model. These are block matrices. But we will define it very soon, and we don't have to worry about it too much, because if we use MATLAB, we just have to write it in the program. We define the matrices, and then we push the enter button, and then MATLAB is doing the calculation. So we don't have to do it hand by hand. We just have to know what is behind. So what is behind this formula that we employ. And again, so we see here that this guy here, this whole guy, is inverted. So what it actually means is there is something, this guy here and this guy here, they are in the numerator, and this guy here is in the denominator. So there's something in the denominator. But we will figure out that very soon, what's going on here. So that's the formula, and now what we have to do is we can break it down and step by step define the matrices. So our test statistic, because we have obviously we are interested in these two guys here. So our test statistic is distributed as a chi-square distribution with 2 degrees of freedom. So this lambda here, in our case, lambda is distributed as chi-square with 2 degrees of freedom. Because we test 2 parameters here, and we have 2 equations. So obviously all this is belongs together. Okay, if we have 25 test assets, we have 25 guys that we test jointly, and then this guy here would be distributed as chi-square with 25 degrees of freedom. So all this depends obviously on the number of parameters that we test, which in turn depends on the number of equations that we have. And now we need to break everything a little bit more down. So let's start first with our sigma hat. Yeah? What is that? Yeah? So what's our sigma hat? This capital sigma hat, question mark. So let's take this, this we can take away. Yeah. We have to remember it, we will remember it here. -2. So first of all, for each single equation, yeah, we have, as I already said, we have the same regressor matrix. Yeah? And our regressor matrix looks like this. So we have our x, we define our regressor matrix x as, yeah, we're having ones in the first column, yeah, which is the t/1 vector, and in the second column we have the observations of our x variable, x1, x2, until x capital T. Yeah? So that's a t/1, t/2 matrix. So we have also defined our vector y. Yeah? So y1 is a vector of that has the excess returns. Yeah? The observations y1, y2 until y capital T. Yeah? So we have defined our y1 vector, our x matrix is defined. So we run OLS, our well-known formula x transpose x inverted, x transpose y, using these data matrices. What we get is then our, let's call it b hat 1, yeah? Our point estimator for the first equation. So, and that's then given by, so what we get is basically the alpha, the estimate for alpha hat 1, and